The problem is Quaint jet, so I'm just going to remind the problem. When water is forced through a thin slit, the flow sometimes takes the shape of an helix. Describe the phenomenon and explain the dependence on aspect ratio of the helix, parameters of the flow, and shape of the nozzle. So here is our experimental setup. So we didn't have any manual pump that we could change the flow rate. So what we did was to use a manual flow regulator with some a tube with a height, and at the end of the tube you have the slit that creates the helix, and we changed H to change the flow rate, and we have a high-speed camera to record all this. Okay. So next, the slits we use. So we 3D printed slits. We wanted to have some laminar flow at the end. So we used some something to make the flow converge. And we use different types of slits. So rectangular ones, ellipse, triangular, and some weird shapes. But we might talk about this later. And for the splits and the fluids, we'll use the three fluids to change the parameters. So water, Isopropanol to change the surface tension, which is really low, and Glycerol to have a higher viscosity. And we also use different heights, so a range from 5 centimeters to 100 centimeters, and we have to change the speed of ejection. So actually the problem says that you have an helix, but what we observed is that for symmetrical slits, in theory, you don't have any asymmetry, so there is no point of having an asymmetry after the slit. So what we actually happens is that the slit is quite weird, and for water it's a quite unstable fluid. So if you look here, it's videos for rotating a slit, and so at the top you see water with a high speed, and you see that it doesn't really converge at the middle, whereas in the second one it's much more neat. And when you make the fluid more viscous for Glycerol, what you get is that you have some damping in the tube, and so you really get the sheets now once again. So we're not going to focus on the helix because the helix is just asymmetry in the slit, and so we're going to focus on the symmetrical slits. So the global phenomenon is represented here. We can decompose it in 3 parts. So the first part, we have some constant angle at the beginning, where you see that the top is the slit in one direction, and the other one is just rotated from 90 degrees. And so we have some constant angle, then we have some curved shapes and droplets formation at the end. So first we have a model for before impact, so we see that the angle is quite constant here. And so we say that we're going to try to find some answer to the constant angle. So we use some model that is a really simple model from the literature, and it says that the thing on the side comes in the middle due to the surface tension, and you have the equation of motion, and from this you can derive a constant speed, and the constant speed is really interesting because it gives us a constant angle. And so if you fit this on the data for a rectangular slit like this one, so we get a quite good fit with what we want, and actually the angle is proportional to the square root of the Weber number. And now we change the height, because in the formula, the Weber number has a length, and the length is the size of the slit, so the height of the slit. And if we change the number, and here I plot it differently than before, I plot alpha as a function of u0, and the prediction is the shape, and I got 3 measurements every time, so it fits pretty well. So for the first part, we're quite happy with what we get, and then we get some oscillations. And that's really interesting because it really looks like a damped harmonic oscillator. So can we do something to modelize it very easily? So we have force bringing the shit back, the surface tension, the water wants to be into one jet, and then you have the dissipation because it oscillates on lower and lower heights, and that's the viscosity. So let's try to model this with some scale law. We have a few forces. We have the surface tension, the viscosity. The gravity is orthogonal to the speed. And what I do is that I'm not plotting dv as a function of dt. It's going to change to be a function of x. So x is on the axis line, and I want to have some function to describe this oscillation this oscillation of the shape of the jet. And so if I do the equation, I get some equation like this, and we see that we have we have the damped harmonic oscillator equation, where viscosity acts as the dissipation force, and the surface tension is the one that brings the oscillator back. So when we plot oscillations, we see that if in the experiment before, if I try to fit some oscillator with the parameters I use A and B to fit the oscillator, it really fits really good, but you can't fit it before because it's another theory, it's the constant angle theory. And so just to get more sense about the physics that goes on there, what happens if we increase the eta here? Is it really going to be the force that is going to make the fluid dissipate energy? And so we plotted this for two fluids with the same speed and the same slits, but for glycerol, which is going to normally dissipate more energy than water, what we actually get is on the second rebound, we see that on the right side it's water, and it's going higher than the left side, the glycerol. I can still fit my oscillator, and I see that the viscosity here takes the role of the more attraction. So we got the model before impact. We can write it as a function of Reynolds and the Weber number. And actually, to really understand if it's not just fitting for every parameter and just finding some random thing, we try to predict the value of eta and gamma, so the surface tension and the viscosity, which are hidden in the Weber and Reynolds number, by just fitting on two parameters and keeping these parameters constant for every thing we did. And so here is what we get. So it's a logarithmical scale, and on the axis it's the viscosity, and on the y coordinate it's the surface tension. And we see that it's a logarithmical scale. So if I'm in the middle, I'm less than one order of magnitude out of the prediction of the surface tension and the viscosity. So I see that for isopropanol and water, I get good fit with my theory, and I keep alpha and beta constant, and that's really important. Then for glacial water, I also get some good fit with the experiments and the same alpha and beta. And also, that was for the problem, but they wanted the aspect ratio of the helix, and so for this model, you can really get it quite easily. And you get that the lambda, so the length of the helix, some teams might have found that it's a square root of the Weber number, but actually, if you don't have the viscosity, that's right. But if you have the viscosity, it's a different length, and I just wrote it here on the right side. And so now I wanted to go back to the helix because that was the problem, and actually we didn't see much difference when we plotted. So what we did, so I don't have it on the slide here, but if I look the slit from the center, so I'm going to draw it here. I'm going to have this thing, and so what we did, we curved some circles here, and we actually put some angles before they went through the slit. And so what we see is that at the beginning, we still have on the top, you still have the sheets that are happening, but when you reach some critical velocity, the flow changes and you take the shape of an helix, and you see in the lower part that you don't really have the shock in the first crossing over here, because otherwise the next sheet would be in the other plane where it's not here. So that would, and actually when we plot some things, we don't really see any difference, because the only difference that can happen, actually, it's the theory is a good way to represent the helix, because the only difference that could happen is the dissipation of energy that really happens when you have the encounter between the fluids. When you have the encounter between the fluids at the shock moment, and if you have an helix, you never have this shock, so you dissipate less energy. That would be something we can try to go further with. Just a few words on instabilities over here. So actually, when you do for high speed and the jet, the side of the curved shape is destabilizing, and that can be really studied quite easily with the Rayleigh-Plateau instability. That's Rayleigh-Plateau instability because you just measure the wavelengths between the two droplets, and you see that the other candidate would have been the Rayleigh-Plateau instability with some fluid pushing out and creating the the destabilization with the air, and from literature you get that the length is too big compared to what we observed in practice, which correlates with the relative instability. So I'll just conclude with this slide to show that we were quite satisfied with the way we explained the whole slit phenomenon. Thank you.